Hi everybody, welcome to this new season of the OpenHT live stream series. So, as you can see already, we are not on KiCad today, and we won't be on KiCad for some time now. So the board that we finished 10 days ago is now in production, so we are waiting for it to be produced, and then we will be able to try the firmware on the board. So right now we only have the nucleo board in our hands, but there is a lot that we can try to use on the board without having the proof of concept already. So as you may have seen already, Jae K5JAE did a first version of the GUI that we are going to use. So it's using the LVGL library, and of course there is still a lot to do on the low-level side of things. So that is all the low-level functions that we are going to use to interact with the devices, the hardware basically. So one of the first things that we can do and that we are going to try to do today is try to use the MEMS microphones that are on the board. So if you have a look at the nucleo board, with this side the mini USB on top, you have right here one MEMS microphone, and here you have two. One which is about in the kind of in the middle, and another one right here. So those are what is called a MEMS microphone, and MEMS stands for micro electromechanical systems, if I remember correctly. So that means that it's basically a silicon chip which embeds a very tiny electromechanical system. In this case, it is the silicon which moves and detects the sound waves that are hitting the microphone. So nothing to do with classical microphone, which uses different techniques, usually membrane and so on. So you don't have any membrane in those. The way these work is that you oversample the signal that you are trying to capture, and for each sample you only have one bit, either 1 or 0. And this kind of signal is called PDM, pulse density modulation. So basically you have to count the number of ones that you get in your stream, and the more you have, the higher the pressure. And if you have like only ones, you are at maximum pressure, sound pressure level. So you are saturating the microphone, and if you have only 0, then you are saturating the microphone too, but with kind of a negative pressure if you want. So you are in the bottom part of the sound wave, where the pressure is below ambient pressure. So the way this works is that you oversample it, and then you capture maybe 16 samples, let's say, for one classical audio sample. That so by classical audio sample you can understand like a WAV file sample, so for example, or so yeah, you have lots of samples, and then basically you have a whole algorithm that is gonna have to run on the board to low pass filter it and remove the DC offset and so on. Okay, so that's a rough explanation of what we are going to try to do today. I already had a look at it earlier today, and yeah, the way this is all arranged is kind of strange. So let's have a look quickly maybe at the schematic of the board. So this is the schematic of the nucleo board. Basically, you see there is the MCU in the middle, and then all different kind of peripherals on the side of it. So On the top right is the SD-RAM, which is what we are using to store the graphical buffer, for example. On the top left is the audio devices with an S, and which we are going to have a look at. Then you have the LCD screen, you have QSPI, which is a NOR flash, which is used to store the permanent settings or the user settings and so on. You have the micro SD, you have a few LEDs, you have USB, you have the connectors, of course. Another series of connectors. Then the ST-Link, which is the chip on board, which is used to debug it, program it, and so on. And the power supply and so on. So we are going to have a look at the audio device today. Hi Mark, what are you using, Windows or Linux? I'm using Windows, yes. And this is the IDE that we are going to use for the proof of concept for now, because there is lots of boilerplate code which is taken care of by the IDE. It's not ideal, it's not perfect, and there are a few bugs in it, but it's enough for us. Hi Wojciech with no audio. So, okay, this is what the audio looks like. So in the middle is, we don't care about it now. This is a big chip which is used to create the audio signal to the speaker or to the jack for the headphones if you have some. So yeah, we won't be using it. So the goal today would be to try to record my voice and try to see if I can read it back on my computer. Okay. Turn your speakers up. Who are you talking to, Steve? Is it Wojciech or me? Okay, and in the meantime, I'm gonna try to get it started with some music, maybe. Oh yeah, I have to go back in time on the channel, on the Discord channel, to try to find the playlist that we were using. Just give me a short moment. Where was it? Wasn't it? Oh yeah, it's here. Okay, great. Let's pick that playlist up and go all the way down so that we don't listen to the ones that we have already listened to. Happy Travel. Okay, seems nice. Yeah, that was for Wojciech. Okay. Oof, not me. my sound settings are correct. Okay, great. Alright, so I just said that the big chip in the middle here, we don't care about it now, and what we care about is the three on the left. So this is the standard way to use a MEMS microphone, actually. So you have the supply, the power supply on the left is VDD and ground. And on the right you have the signals that you use to interact with it. So you have an LR pin, which LR stands for left-right, basically. So that means that the microphone can output his sample either on the rising edge or the falling edge of the clock, which is provided on CLK, pin 3. So I don't remember which one is which, we don't care about it right now. let's say that if you put LR to VDD, then you will output your sample on the rising edge, and otherwise it will be on the falling edge. So the out is where you take the sample. So you have the mic CK, which is the clock that you feed to the microphone, and mic data, which is where you read back your data. So there is a catch, however, which is that what they advise to use usually would be an I2S peripheral, which is kind of an SPI bus for audio, except that we won't be using that, but they code it that way too. So let's have a look maybe at an application note written by ST, which explains a bit what we are gonna try to do and why. So if I remember correctly, it's on page 18. Okay, right here. So you can see that we have the two microphones on the right of the diagram. So one is used for the left audio channel and one is used for the right audio channel. You have the clock inputs for the microphones and the data output. So basically the thing is that if you set your left and right channels correctly, then you won't have any problem with the output colliding, because when it has to write on the falling edge, then whenever there's a rising edge, it's gonna go in high impedance output, so it's not gonna mess with the output signal, and vice versa if you're on the other channel. But you see that you have your I2S or SPI, which is the kind of thing that can be a bit confusing. You have the data input and the clock output. However, the clock output does not go directly to the microphones. It goes through a timer, which is configured in slave mode. Basically, what this timer is used for is it divides the frequency of the clock at the input. So you can see basically you have the input here, you divide it by 2 and you have the output. Why is that? It's because the SPI bus is gonna sample the data here only on the rising edge. But if you remember correctly, because of the left-right channel selection, your microphone can write on the falling edge while the SPI reads on the rising edge. So what we need to do is divide the clock of the microphone by 2, so that for each rising edge of the SPI bus, we are gonna read a different channel. Okay, I hope you got what I was saying. It can be a bit confusing, so don't hesitate to ask questions if you have. So that's what we are gonna try to reproduce today, and if everything goes well, we should be able to sample the microphone, use the provided algorithms to decode the PDM data to a PCM data, which can be used to write to a file. And so what we are gonna try to do is write the audio to the micro SD card and then read it back on the computer. So the board is for now running FreeRTOS using CMSIS API. So I'm just throwing words at you. Maybe you know what it is, maybe you don't know. Basically, FreeRTOS is a real-time operating system which is used in lots of embedded systems. It's very easy to use, very simple, and provides all the communication method that we need to communicate across the tasks that may be running on the device. And CMSIS is basically an interface which is kind of a wrapper around the FreeRTOS API, just because that's what ST provides by default, and let's not worry too much about that. Okay, so I'm just gonna reset this file because I messed with it before starting the stream, and I'm gonna check if I need to reset the file on the drive, on the disk too. It seems that everything is correct. Okay, so All right. We okay, we are gonna get started. So first we need to configure the peripheral which is gonna read the data from the microphone. This peripheral, it's SPI3. Yeah, okay. Here, SPI3 mode. Then we are in half duplex, and basically we are only receiving. So receive only, and we are the master because we drive the clock. So the sample are gonna go out whenever we decide. Which pins do we need to select? Well, let's have a look at the schematic. So mic data, it's the sampling, the pin that we are gonna sample. So mic data is right here and connected to here, PD6. So we are gonna have a look. Okay, PD6, it's not good. Master in slave out, that is the pin that reads, that is sampled by the SPI peripheral. So let's just find, sorry, let's PD6 right here and configure it as master out slave in. No, that's not. Yeah, of course. Oh no. That's gonna be annoying. So we need to use it as I2S3 SD. However, we can't use the I2S peripheral for another reason. Oh, that's gonna be very annoying. How is it that the I2S peripheral can use oh god. The I2S peripheral can use the SD pin to sample, but the SPI bus can't. So that means that we wouldn't be able to use the SPI bus, we would need to use I2S3 bus. However, you can see that it's in red because we have something which is the transceiver reset pin on PA15. So that's very not good. So this is a completely stupid situation actually, because the I2S3 peripheral does enable a third pin that is never used. So if I put it in half duplex master, just gonna put the configuration, one configuration that I think is right. We don't care about that now. You can see that we have PD6, which is the clock and the data input, SD serial data. We also have PB3, which is the clock, which I don't know if it's the one that we are going to use, but anyway. We also have WS, which is word select, which is placed on PA15. But we are never going to use that signal. Never, ever. And if we try to disable it, then the peripheral disables itself. And I don't think that there is any other pin that we can route the WS signal to. So that means that as of now we are not able to have the the reset pin at the same place as the I2S3 WS. Yeah, let me just have a look. Maybe there is another pin to which we can route the WS output, and then we could, but I don't think there is, otherwise it would have allowed us to enable the peripheral without removing the allocation of the pin. Hi Andy, how are you? Okay, so right now it means that either we are gonna be able to force the WS pin to be always high, or we are gonna have to patch the board. It doesn't seem like we can route the WS pin to any other pin, or at least not to any other free pin. And this is completely stupid because it's gonna force us to enable it, but we don't need it. And the I2S peripheral is able to read from the pin that we use, but not the SPI peripheral for some obscure reason. Okay. Let's have a look at the data sheet, maybe. Is there anywhere where they describe the IOs that we are? Oh yeah, I think there is. No, but let's have a look. Maybe there is a trick that we could use. If we use SPI 3, yeah, of course we're gonna need to reset that pin and use it as a half duplex master. Oh, then okay, so we could configure the SPI bus as a half duplex master and only use it to read, I guess. Let's have a look at the datasheet, what they say about this half duplex master mode. Half duplex. Okay, I guess they put a 1 kilo ohm resistor in case one wants to write a 0 and the other one wants to write a 1, in which case it would short the pin to ground. But we know for a fact that our device is never gonna try to read from this pin, and if we configure it to only read on our side, it should be okay. No problem ever, so don't worry about it. Okay, okay, I think that's what we are gonna need to do, otherwise we are gonna have big troubles. PA15. Let's PA15. Okay, I'm just gonna close without saving and reopening it. So we have a theoretical solution. Half duplex master. We don't have any hardware slave select. We don't need any actually. Parameter. It's an LSB first, data size 16 bits, frame format we don't care, prescaler, yeah, then we are gonna need to check the baud rate, which I don't remember what we have to use. The slave select, so NSS, the first N means that it's reverse polarity, and SS means slave select. So that means that you select the slave not by writing a 1 but by writing a 0. CRC calculation, we don't need any. This data is not tied to any kind of CRC or whatever. We are gonna need a DMA for the SPI3RX. I think we are gonna need are we gonna need a circular or normal DMA? I think I don't know, we are gonna figure that out later on. Let's keep the goal not too high for now, otherwise we are gonna get lost in very confusing things, I think. Okay, so now we have a way to sample our data in. What we want to do is provide a clock to the microphone. For that, we need to go through the timer number 4. It's not me who chose that, it's on the board, that's the way things are. So if you have a look here, you have I2S3CK, which is in our case SPI3CK. Sorry, it's confusing, which is linked to PB3, and PB3, if you have a look, just let me a few seconds to find PB3 on this screen. PB3, is it? I'm getting confused. Yeah, PB3. Too many signals. Where is it? Okay, let me just be sure that we haven't used it for anything else. No, PB0, PB1, PB2, so PB3 is 3, and PB3 is where is it? It's hidden. PB7. Or is it oh yeah, sorry, PB3, okay, no, alright, so it's the clock output. So, is it? Yeah, okay, it's the clock output, which is in turn connected to... Sorry, this schematic is very confusing. I've been having a look at it for a few... Yeah, okay. I2S3CK is connected here, so which is connected to PD12. So that means that PD12 is connected to PB3 via a label called I2S3CK. Oh, can I really? No, that doesn't seem to work. Not in the way I understand it. So if I want to... Oh, maybe here. Ah, yes. Thanks. Bottom right corner. I'm gonna use that a lot, I think. Okay, I was saying that PB3 is connected to I2S3CK, which is connected to PD12, which is an input for the timer 4, which is why we have to use timer 4. So we are going to use it in, I think, trigger mode. Those are settings that I read from the board support package that STM wrote, which we are not going to be able to use, so don't worry too much about it. So we have channel 1, which is our input. Channel 2 is output. PWM generation channel 2. And then, okay, what I hope is that I can put a 0 here. Okay, lots of things that I don't really understand here. Let's have a look. Right here is where they initialize I2S. What I want to see is how they initialize the timer, which is right here. Okay, yeah, we are in it. Okay, so period is 1, but we need a period of 0. So in the BSP, they sample the 2 microphones, so it means that they have to divide the clock by 2, but we can't divide the clock, we don't have to divide the clock, otherwise that means that on each complete byte only 4 bits are gonna contain data, and we don't want that. We want mono signal, 1 channel only, and so we want to use the whole 8 bits from a byte, or in this case 16 bits from a word. Counter up, alright, that's what we used here. So prescaler 0, period 0, counting up, internal clock, no division, so clock division 0. Auto reload, I guess we are gonna need auto reload, otherwise it's not gonna restart, and it's only gonna do it once, I guess. Maybe I can do we okay, auto reload preload. Yeah, I would like to see if What are the default values for those? Well, I guess we are gonna have to need to have a look here, and timer 4, which one is it? Timer 4, 2 to 5, 2, 3, 4, 5, right here. 16-bit timer 4 input capture is what we are gonna use, blah blah blah. Okay, what I want to have a look at is registers. Auto reload, preload, enable, Bit 7 defaults to 0. Registers are not buffered. Okay, I don't. Maybe we just don't need to modify that, I don't know. Trigger outputs, master slave modes. Do they have something resembling that in the code? So input trigger, which is TI1, FP1, and which is what we selected, TI1, FP1 as the trigger source. Slave mode external 1, and I don't know how that translates to any kind of configuration. Okay, don't need any delay, I guess. Trigger event selection. That maybe we need to configure. TRGO. I don't think there is anything resembling that. Oh, I hate it when they don't have the same macros as ETR polarity non-inverted. What does that mean? Okay, what a mess. Let's just say that it's a mess. Okay, I'm just gonna try to keep it as is and see what codes it does generate for us. So let's go. I'm gonna need to, so there is a problem with the code generation for the micro SD card. So that means that in the SD disk.io.c file, there's this header which is missing for the RTOS interface, and I added it manually, but then each time I regenerate the files, then it's removing it. So you just have to know that. Okay, let's have a look right here at the timer initialization TIM4. Okay, it's gonna be also, let's collapse all those. All right, here core src main. Great. Place it on the right panel. And let's see where the timer generated code is. right here. Perfect. Oh no, I'm gonna place it on the left part of the screen and compare it with this one. Okay, so instance team 4, which is the audio team is team 4, trust me. Prescaler, okay. Counter up, period, okay. Clock division. Okay, what is the value of this one? It's 0, okay. Auto reload preload, which is 0, and I guess it defaults to 0, but they don't initialize it here. Then base init, which is called somewhere, I guess. Where is this defined? How the hell? So you have IC in it. Oh, for input capture and base units. Okay, did I miss something? Slave mode. Would this be it? I don't know. I have no idea what I'm doing. Just gonna try a few things until it seems to work. Then, oh yeah, we are gonna also need to set the GPIOs, but first this. Yeah, okay, let's see what it does. Because I don't know how to configure the input capture part of it. I don't think gated mode is what we are looking for. Still have base inits, which is not what they use. How do you configure it in input capture? Ah, maybe like this. And then that means that we would have trigger mode, maybe. No, external clock mode 1, channel 1 input capture, and PWM generation channel 2. Huh? Okay, yeah. Anyway, let's retry this set of parameters. I really hope that we are gonna be able to have something kind of working today. It would be nice. So, still base in it. Ah! Something appeared. Okay, then we have PWM init. Which they don't use either, so okay. It seems that we have the reset mode right, maybe, but then I have no idea. Those timers are supposed to count, but they are so complex. Maybe it's not a PWM generation output compare, maybe. Okay, I'm gonna try this last set of parameters, and then we are gonna have a look in the datasheet. Otherwise, it can take the whole evening just trying settings at random. Slave mode reset, slave mode external 1. So what does the datasheet say? Input capture, so basically you read from a pin, I guess. Okay. So yeah, datasheet is quite a lot to read. You have the music in the background, so yeah, let's stay happy. So we know that we are in up counting mode, and we are not gonna focus too much on this. That's less pages to read. Clock selection. Okay, so it seems that we will be in external clock source mode 1, maybe? So this mode is selected, blah blah blah. The counter can count at each rising or falling edge on a selected input. So our input would be channel 1, and we count whenever there is a rising edge on channel 1. Because yeah, internal clock source, that wouldn't be it. So, for example, to configure the up counter to count in response to a rising edge on the TI2 input, use the following procedure. So that's what we are doing, except that it's not TI2, I guess it's gonna be TI1. Configure channel 2 to detect rising edge on the TI2 inputs. So, yeah, that's in input capture. Sorry, it's getting a bit narrow. Input capture, I guess in direct mode, it's the only one that we have. Yeah, the thing is that there is quite a difference between what you read in the datasheet and what you can enter in the CubeMX utility. So sometimes you are in this kind of setup where you don't know what is really what do you really need to do. Trigger source. So they use TI2, but we would be using TI1, so TI1 FP1 as a trigger source for the counting. That's a lot of circuits. Input capture mode. Okay, that's quite convoluted. Timers and external trigger synchronization. Reset mode. Okay, that looks like what we would need to use, I guess. So So we have reset mode or gated mode. Then gated mode, you only enable the counter depending on the level of the input, which is not what we need to do. Trigger mode. So slave mode trigger mode and slave mode reset mode. Nah, reset mode doesn't look like what we need. It looks more like trigger mode, I guess. Slave mode, external clock mode 2 plus trigger mode. Man, that's not fun. So are you keeping up? Sorry, not this one. Generate code. Okay, that's very confusing. I thought that it would have been more easier, and then we would have been able to do more today, but maybe not. What does the code look like? Timer IC config channel, input channel priority rising. They put it in priority falling. So put channel 1. Where do I even change that? Okay, yeah, Mark, you will be able to. So for now, the code, there is 2 branches on the GitHub. One which is the main, which was the one on which Jae pushed his changes, and then I started various things and tried a few other things. So I switched to another branch which I called HAL implement, because basically I wanted to implement a few things using the HAL, but yeah, both should for now work. So you have the GUI first version, and if you press on the blue button and you have a micro SD card in the micro SD slot, it should save screen capture, but it's buggy for now. The logo doesn't display correctly. I think it's a bug in the LVGL library. Okay, so IC channel, IC prescaler is div1, yeah, okay. Oh, TRC, and they use direct TI. So maybe that's why we don't have the correct settings. TRC, TI, so why would it be? Trigger source. I have no idea what trigger source I should use. That's very confusing. Team slave mode external one. Yeah, that would make more sense like this. External clock mode 1. And then oh yeah, trigger. We said falling edge. Output compare. Output compare PWM mode configuration. Like this? No, I don't think it's output compare mode. Team OC mode PWM1. Is there anything resembling that somewhere? Okay, let's... In the end, I believe that trying to copy the code by having a look at it is more efficient than having a look at the datasheet. Okay. 0 and fall. Okay, it's definitely not the same thing. However, slave mode, so we are in the correct slave mode, it seems. Is it? Clock source. Ah, that's so annoying. Slave config synchro. Clock mode 1. So the input trigger, it's correct. Slave mode, it's correct. Oh. Yeah, of course. So we are calling the same function, except that they use old code that they didn't rework, so they use a longer version of the same function because screw, that's why. Trigger filter 0, 0, okay, polarity non-inverted, which is 0, and we are using falling, which is 1, so it's not right. Let's see if we can flip that. Trigger event selection. What should that be? So that's why it's so hard to use nucleo boards, actually. STM does make great products, but their documentation is really bad. And they have a support forum, and yeah, even them don't really use it. It's as useless as it can be. Master config synchronization. Nope. We don't want any master config synchronization. So something is wrong again in the configuration. If you do that, I don't know what it does. Oh yeah, of course, then it's not gonna output anything. So yeah, we just as a reminder, we are trying to make the timer divide the input by 1. So basically just a pass through, actually. And I don't know how to do that. We still have the master config synchronization, which we don't want. Did I regenerate the code? I think. So I guess I messed up something here. I'm getting lost and confused with what settings I already tried or not, so sorry, this is a bit weird. Oh, OC mode, PWM1. Oh, that's what we need. Great, okay. Pulse. Pulse, they use 1. Which is it? Yeah, I guess it would be that one. I don't know what pulse means, but let's use 1. PW1 mode 1, fast mode, I don't know. Do they use a fast mode? Disabled, okay. Channel polarity, high, great. Output compare preloads. We are getting closer to the configuration we need, luckily. I still don't understand why we have suddenly a master mode which appeared. Config clock source. Do I have? I haven't. Select external clock mode 1. Yeah, that's it. And I don't understand why they have this. Oh, but no, we are using timer PWM init instead of IC init. Okay, let's get back at it later, and by later I mean I'm gonna have a look off stream, and we are gonna try that later on. It's already 10 o'clock, 10 p.m. So I'm not gonna be too late today on stream. So let's try to see if we can generate some code maybe that would be able to use that later on. Anyway, so that I just said that we needed SPI 3 half duplex. We are gonna have DMA1 stream 0, and yeah, okay, so I'm gonna go, okay, I'm gonna create a new FreeRTOS task. So right here, tasks and queue, I'm gonna add the one task which I'm gonna call microphones. Priority, we are in real-time priority. Stack size 256. Entry function. Save and generate the code. Something is wrong. What is it? Heap usage. We are using the maximum amount. Is it? Total heap size. I guess we can allocate much more than that. How much RAM do we have available on this chip? Let me see, maybe it's on the first page with a bit of luck. Okay, we have 384 kilobytes of system SRAM. So we can use more. So let's double that. Tasks. So we have this, okay. Also, we are gonna use the PDM to PCM. And we need CRC IP, why not? If you need it, take it. Channel 1. LSB. Are we in Big Endian or? I have no idea. Anyway, high pass tap. We are gonna have a look at that later. We have only one channel on the input and one on the output. Decimation factor. This, yeah. Hi, Dix BTV. What's up? Doing fine, and you? We are trying to do the firmware of the OpenHT proof of concept, and it seems that you are the first viewer on Twitch that I could find, so maybe you got lost and are wondering what you are doing here. Output sample numbers. So number of PDM samples to generate. Let's use 16 for now. Okay, let's keep it like this and generate the code and have a look in the main file at the task what we are gonna need to implement. So the main function is gonna do for us all. No, we are in the wrong. Let's close that for now so that we don't get confused. The main is here. We don't need all these. Okay, so in the main file main function. Okay, so it does take care of initializing the PDM to PCM, the CRC, the timer, and the SPI bus. Great. And we have the start microphone task here. And that's where we are gonna need to initialize what needs to be initialized. And also do the call to the functions to convert the PDM stream to a PCM stream. Function implementing the microphone thread. What did I... Oh, that's surprising. Tasks. Oh yeah, I just called it task my microphones. That's why. So, I do believe that the function in the main function is, so this one, it does, I think, initialize everything we need for the PDM to PCM, does it? So it does use PDM buffer and PCM buffer. Oh, no, it's this one. Oh, is it somewhere? Oh yeah, okay, here. It does initialize everything. The filters and so on. And then we have the MX PDM to PCM process, which is the one we need to call every now and then. Except that it does not do that. Why? What the heck? So the MX PDM to PCM process does nothing. Oh, maybe it's okay. Oh, I'm getting so bored with this. So bored. Why would you define a function which would just return an error and that's it? Oh my god. So those functions are, I guess, implemented in the libraries below, which, yeah, it's binary files, so we can't read them. So that means that we are gonna have to have a look at some application notes from STM. So here it is. Blah blah blah. It explains everything on how it does that and so on. So this is all the functions that it does implement. So this one is initialized all the static memory, default values, blah blah blah, set config, so that we use to set the configuration on of the library. So filters and so on. Get config, we don't need that. De-interleave. Oh, that's nice. Not yet implemented. So we don't need to de-interleave anything. But why on earth would you do that? Am I the only one getting very, very confused with what they are doing? Hi Bastien, how are you? So we are doing some code, but STM decided that it would be very hard to do, so we are just trying to write some code. So we have PDM1 filter handler, which is defined here. So that means that so we are gonna need a way to signal to our process, to our thread, that it must process the samples acquired. So that would be using some kind of event, I guess. Let's try microphone acquisition complete. Let's try to see if that's what we use, if that's what we need, but because of course, so one of the good thing with the CMSys API is that the documentation is really not as good as the one on FreeRTOS. The FreeRTOS documentation is very good, very well documented with examples in the pages, but you have all the explanations on what it does, why it does that, and in which case you may want to use that. But CMSys, not as good. What does STM use? CMSys. So let's keep using that. So what did it create? Okay, OS event flag ID. Yeah, of course. So it seems so all the CMSys documentation is on the Keel website. I think they are the one who created maybe CMSys, I don't know. So it seems that the event is what we need to use. That's really what it looks like. So we will have this thread, which won't be a thread, it's gonna be some kind of interrupt, which is gonna be fired every time we have acquired enough samples. Oh, we are gonna need so what we need to do is fire an event whenever the PTT is pressed. And whenever we detect this event, we start the microphone data acquisition, and then whenever we acquired enough samples for the filter, we also check if we still need to start a new acquisition. So if the PTT is still pressed, I guess. So that means that okay. First of all, okay, it's gonna make for a weird programming style, I believe. Oh, thanks, Bastien. I'm doing fine. I'm reading your message a bit late, but yeah, it's trying to stay calm facing STM32 madness. Yeah, it's already past 10 p.m. What I'm gonna try to do is quickly switch the microphone processing thread to an external thread, and we are gonna start compartmenting it in different files. So this code generation option as external. Just gonna go here. Like that, and generating this is gonna disappear, I guess. It did. Great. So in the source files we are gonna have new what source file, yeah, okay, sorry, source file that we are gonna use called task microphone.c, and the new header file that we are gonna call task microphone with H. Okay, and we don't need this, we don't need all this. Yeah, and then of course, because it declared it as external, it's gonna be weird if I replace it in the H header file. So yeah, you see that now the start microphone task is defined as external. And also, yeah, here is where they started, and yeah. Okay. let's place it in the H file anyway, so that it's not too weird. In here, what we are first gonna do is do all the initialization. Which I don't really know what we are gonna need to initialize for now. Then each task, so the way a FreeRTOS task works is that you have first, you call a function and it's gonna work inside that function every now and then it's gonna stop the processing in that function, get out of it, go to another function, and this is all transparent to the user. This is called the scheduler, and the scheduler is the one that is smart and decides whenever it must execute which function, and there is there are loads of rules which decides which function to execute when. So you have the first part of the function, which is before the infinite loop, and this is where you place everything that you are going to execute once for your task. And then you have the infinite loop, which is the working part of your task, so everything that you need to do repeatedly, because in an embedded system usually everything is repetitive in a way. You need to do it every now and then, be it a few days or a few milliseconds. So in our case, we need to first include the cmsys os.h header file, and then we need to get an event flag. This event flag is the one which is defined in the main. This is the mic hack complete event flag. So this. OS event flag IDT, OS event flag IDT, so mic hack complete handle. So basically that means when we are doing an infinite loop, we are waiting for somebody to tell us that I'm done with the data acquisition from the mic, please start your processing. Then we are gonna do our processing. It's gonna run for maybe a few microseconds, let's say. Then we are at the end of the infinite loop, we start at the beginning again, and then we need to get the flag again. But because it have been because the flag have been reset by us getting it, then we are waiting for it to happen again. Or maybe we need to wait for it and then get it? Okay, let me check. Because there is the wait and the get function, which I don't understand the difference. Oh, my bad, that's not the function that we need. So that's indeed wait. So you don't, okay, yeah, you don't get an event flag as you would get a mutex, for example. So, okay, so we need to wait for it. The flag to wait for. I don't know. Okay, for now, let's not think too much forward. OS event flag. Wait. First, let's use flag. Oh, sorry. Flag wait. Flag, let's use flag 0, I think we can. Options, I don't know. And timeout, OS wait forever. So that means that, so sometimes you can wait for something, and then if it didn't happen in the next 5 seconds, then you keep going and do something else, for example. So this is a possibility, but in our case, if the event never happens, that means that we don't have any data to process. So options, what is it? Oh, flag no clear, but yeah, we do want to clear it so when we read it, so that we can't read it twice in a row. Okay, basically we wait and then we do, so we will need to include pdm to pcm glo.h, I guess, and then pdm filter data in, data out, handler. Okay, so I think we said that we were processing 16 samples every time, so yeah. Is there anywhere where we have this 16 value defined? I don't think we do. What a funny name. Okay, yeah. I believe that I'm gonna prevent the code from the CubeMX from generating PDM to PCM functions, if I can prevent it at least. Generate code, we don't want that. So this file, yeah, it's as good as useless. Maybe we can at least call this function. Yeah, those we need to declare them as external in the microphones task. We are also gonna need to define two buffers, so we need to include main.h to have access to HL libraries and so on. So filters, handler config, blah blah blah. PDM to PCM filter init. No, wait, MX PDM to PCM init. And do we have access to process function? Oh, it's in between user code begin and end blocks. So that means that we could basically define everything in this function. Let's try to keep the CubeMX style to avoid getting people confused. Yes, the M is in STM stands for madness. Exactly. And 32 is because you have a lot of madness, basically. Okay, so that means that here we would need to call PDM to PCM, and yeah, we include that one. Which, okay, I guess we need to build it at least once to rebuild the index or something like that. We have loads of errors, but we don't care about that. Index rebuild maybe. PDM to PC. Oh, okay, PDM filter. Okay, that one. P data in, which will be PDM buff. P data out, which is PCM buff. P handler, which is that. Okay. Great. So basically, actually, in the task microphone, we don't need to declare those as external. We just need to call that one here and then mx PDM process. We are gonna have uint16t array of PDM samples, which I think just needs to be basically very large, because we are gonna need to so if we have, so in the end we also have uint16t PCM samples, which is gonna be 16 samples. So if you remember, we have a decimation rate defined here, I think. Decimation factor 64. So that means that we have 64 more samples in the input as in the output. Sorry, I'm getting lost in my tabs. So I guess we have 64 times 16 here. And so we would have MX PDM to PCM process with PDM samples and PCM samples. So that's very, very basic for now. It won't be working like this, of course, because we need to check for the PTT and so on. Okay, I think I'm gonna leave it here for today. I'm getting tired and I got enough madness for today. Basically, at least we found a way to be able to read data from the microphones without conflicting with the transceiver reset pin, which would have been a shame if we had to be resetting the transceiver while we were reading data from the microphone. Basically, we can record voice but not transmit it. You have to admit that for a radio, you lose kind of a lot of functionality. We discovered that the timer thing is not so simple. And we have started implementing a free RTOS task. I'm gonna have to have a look later on what to implement, how. So that means that we are gonna have to, basically we are gonna have to start the SPI transfer into DMA. DMA is direct memory access. That means that the SPI peripheral is gonna fill the memory buffer by itself without the microcontroller having to do anything. So which relieves us from a huge load. Then once it's done, we are gonna have a message telling us that, okay, I'm done reading the samples, you can process them. Then we are gonna process them. However, we want that to be continuous. We don't want to have a break, even for one sample every time we are done sampling. So I guess that what we might have to do is maybe receive a warning every time the buffer is half done. So maybe, oh yeah, that would be, okay, so I'm blinking the window, sorry. Maybe that we can very quickly check for that. DMA. Yeah, I'm gonna have to read a lot of documentation to be able to check if what I'm doing is correct, but I guess that we can use FIFO half full, and then we would have to check for the burst configuration. But then I would be able to fill half the buffer, process it while I fill the other half of the buffer. And if I'm doing that in a circular buffer, then every time it's done filling the first half of the buffer, it's gonna fill the second, and every time it's done filling the second half of the buffer, it's gonna fill the first half. That seems correct to me. but I'm gonna check for that off stream. I'm gonna try to be a bit more prepared for the next stream and be able to explain to you what I'm doing in real time and spend more time writing and explaining than reading, checking and getting mad. So I hope you enjoyed today's stream, however. So this is it for the first episode of the second season of the OpenHT series. Don't forget the Discord server that we have if you never checked it. Or Matrix server, we have a bridge to Matrix 2. Hope you enjoyed today. 73s to all of you, and